Hello everyone, in this video we are going to discuss about analog to digital conversion. In order to do this conversion, we have two techniques, pulse code modulation and the delta modulation. So before moving on to that, let me clarify what do you mean by digital and analog signal. A digital signal is a signal that represents the data as a sequence of discrete values, whereas analog signal is any continuous signal for which the finite time varying feature of a signal is a representation of some other time varying signals. So this is the difference between these two. Now we'll discuss what I mean by pulse code modulation, and this is one of the most common technique which will be used for converting the analog signal to digital data. So PCM encoder has the following three processes. The analog signal is first sampled, then the sampled signal is quantized. The quantized values are encoded as streams of truth. So these are the three steps we'll do in PCM in order to digitize the analog signal. So before we sample, we have to first filter the signal to limit the maximum frequency of the signal because it affects the sampling rate. And also we have to ensure that filtering should not distort the signal. That means we have to remove the high frequency component which affects the signal shape. So this is how this pulse code modulation is done. So let me discuss in detail about the sampling. Before that, this is the diagrammatic representation of the PCM encoder. So it takes the analog signal as the input, then it will perform the sampling, then quantization, then finally encoding. At the end of encoding process, it will give the output as digital data. We'll discuss all these processes in details. First, we'll start with sampling. Sampling is a process of measuring the amplitude of a continuous time signal at a discrete instant. So here analog signal will be sampled at every ds second, where ds is referred as the sampling interval. And next we have to find out the sampling rate or the sampling frequency. So that will be denoted as fs. So that can be determined with the help of this formula. Fs is equal to 1 by ts. So sampling can be done in three different ways: ideal sampling, natural sampling, and flat-top sampling. So ideal sampling is also known as the instantaneous sampling. The pulses from the analog signals are sampled here. Then the natural sampling, it's one of the practical method of sampling in which the pulse have a finite width which is equal to t. The result is a sequence of samples which will retain the shape of the analog signal. Finally, flat-top sampling. So in comparison to natural sampling, flat-top sampling can be easily obtained. In the sampling technique, the top of the sample remains constant by using a circuit, and this is one of the most commonly used technique. And this technique can also be referred as the pulse amplitude modulation. In short, you can you can call it as PAM. And next, we need to discuss about what do you mean by sampling rate, okay, and why we need to consider the sampling rate or the frequency. So, what are the restrictions on DS? And this questions will be elegantly answered by Nyquist theorem. So, according to the Nyquist theorem, the sampling rate must be at least 2 times the highest frequency contained in the signal, and it is also known as the minimum sampling rate, which will be given by the following formula: Fs is equal to 2 into Fh. So actually we need to elaborate on this theorem at this point. First, we can sample a signal only if the signal is band limited. In other words, a signal with the infinite bandwidth cannot be sampled. Secondly, sampling rate must be at least 2 times the highest frequency, not the bandwidth. If analog signal is low pass, then the bandwidth and the highest frequency are the same value. If the analog signal is band pass value is lower than the maximum frequency. So this is called as the Nyquist theorem. Next, we'll discuss the second process, that is the quantization. So the result of sampling is a series of pulses with amplitude values between the maximum and the minimum. So the set of amplitudes can be infinite with non-integral value between these two limits, that is maximum and minimum. The following are the steps we need to perform in quantization. We assume that the signal has amplitude between maximum and minimum, and also we have to assume that the original analog signal has instantaneous amplitude between the maximum and minimum. Then we have to divide the L zone. So this is achieved by dividing the distance between minimum and maximum by L zones. So that we represent as height delta. Delta is equal to maximum minus minimum divided by L. Then the midpoint of each zone is assigned a value from 0 to L minus 1. Then each sample falling in a zone is then approximated to the value of the midpoint. Assume that we have a sample signal and the sample amplitudes are between minus 20 and plus 20. Then we have decided L is equal to 8, that is 8 level. Then the delta will be calculated using this formula. Maximum is plus 20 and minimum is minus 20 divided by quantization level. So the delta value is equal to 5. So that means the 8 zones are divided in this way. Minus 22 minus 15 first zone, minus 15 to minus 10 second zone, and so on. Then the midpoint of the zones are calculated. Minus 20 to minus 15, midpoint is minus 17.5. Then minus 15 to minus 10, midpoint is minus 12.5. And the remaining zones midpoints will be calculated in the similar way. The next step is we have to assign the binary code for each and every zone. So the number of bits required to encode the zones will be calculated based on this formula. NB is equal to log to L. Here we have 8 zones, so we need 3 bits. So these are the different combinations for the 8 zones. The first combination is 000, second one 001. Then it ends at the last combination 111. So 000 will refer to the first zone minus 20 to minus 15, and 001 will refer to the second zone minus 15 to minus 10, and so on. We'll discuss with an example. Here the value at the top of this signal represent the actual amplitude value, and the first two represent the normalized PAM value. Here it is 1.22, then 1.50, 3.24, 3.94, then 2.20. Likewise, the first row is calculated. In the second row, we have to normalize the quantized value. That means we have to take the mid value of that. The mid value is 1.50. For this also 1.50. Here 3.50. And again 3.50. Likewise, the second row is calculated. Then the third row is the difference between these two. That we call as the quantization error or the normalized error. Then we have to assign the quantization code. And we have to check where this PAM value lies in which particular zone. So this lies in the second zone. Then this lies in the fifth zone. And these two are in the seventh zone. And this is at the sixth zone. Likewise, the quantization code will be calculated. Then finally, you have to find out the corresponding finite equivalent of the quantization code. So this is the final digital value so that we have obtained from the analog signal. Now we'll discuss what do you mean by quantization error. So quantization error is the difference between actual and the coded value. And when you quantize a signal, and it will introduce an error. So the coded signal is an approximation of the actual amplitude value. So if there are more zones, the smaller delta value, which results in smaller error. But if the zones are more, so more bits are required to encode the samples, so it leads to higher bit rate. We'll discuss one example how to digitize the human voice, then how to calculate the bit rate, assuming 8 bits per sample. The human voice normally contains a frequency range from 0 to 1000 Hz. So the sampling rate and bit rate are calculated as follows. Sampling rate is equal to frequency into 2. So you will get 8000 samples per second. Then bit rate will be calculated by the formula sampling rate into the number of samples, or sorry, number of bits per sample. So 8000 into 8, you will get 64,000 kbps, which will convert, you will get 64 kbps. Next, we'll see how demodulation is done by using a PCM decoder. So, in order to do this demodulation, the demodulation in the sense how a digital signal is converted to an analog signal. So, in order to do that, it follows the following steps. So, we use a hold circuit that holds the amplitude value for pulse till the next pulse arrives. Then we have to pass this signal to the low pass filter, so which will cut off the frequency that is equal to the highest frequency in the pre-sampled signals. So this is how this demodulation is done. So these are the components of the demodulation. Here it takes the digital data as the input, then it perform make and connect samples, so that will be given as an input to the low pass filter for smoothing, and finally it will produce the analog signal at the output. Next technique is the delta modulation. Delta modulation will calculate the difference between the pulses. If the pulse at the time Gn is higher than the pulse at time Gn, then it will consider that bit as 1. So 1 is used to indicate the positive value, and if the pulse is lower in value, so it will indicate that as 0. 0 indicates a negative value. So this scheme actually works well for a small change in signal between the samples, but whereas if the amplitudes are large, so this results in a large error. So this is how the delta modulation is done. So it takes the analog signal as the input, and by using the staircase maker, so staircase will be constructed. Then from staircase the binary data will be generated. The staircase rises, it will be denoted as 1. If the staircase falls, it will be denoted as 0. So till this point it rises, so we have considered 1. Then it started falling, so till this point it falls, then it again increases. So this is how the binary data will be generated for the corresponding digital signal. This is the diagrammatic representation of delta modulation and demodulation. Delta modulation takes analog signal as the input, then it will be given as an input to the comparator. Then the comparator with help of the staircase maker and delay unit, it will construct the staircase. From staircase, it will be converted into digital data. Then the reverse process takes place in the demodulation. Here digital data is given as an input to the staircase maker. Along with the delay unit, it will construct the analog signal. Then the analog signal will be sent to the low pass filter for smoothing. Then finally it will produce the output as the analog signal. So that is how the pulse code modulation is done. So thanks for listening. Thank you.